for giving me the opportunity to speak here. Yeah, so I'm going to present a very compact result. It's maybe not as broad a talk as the one we've just previously seen. A result which bounds the size of finite rational matrix semigroups. So this is based on a student summer project we did with 3 undergrads from Oxford, Georgina Bumpus, Paulian Stonescu, and Jonathan Tanner. And I'm mostly basing my slides on Jonathan's talk. So credits go to him, and the other co-author of this work is Stefan Kiefer, who's also at Oxford. Okay, so very brief informal introduction to matrix semigroups. So suppose we're given a finite set of n times n matrices. Then we denote by m bar the semigroup that's generated by m. And so if we just look at a couple of examples, yeah, so here we have a generating set consisting of 2 matrices A and B. And we see if we square A, then this remains A. B is defined like that. And the semigroup generated here is a finite semigroup. It includes the 0 matrix, etc. And these are the elements. Of course, matrix semigroups, I mean, any group is also a matrix semigroup. So for instance, if you look at all sign permutation matrices, then this is also gives us a matrix semigroup. And an example of an infinite matrix semigroup is given by the set M here, consisting of matrices S and T. Yeah? So these 2 matrices, they generate the set of all invertible integer matrices, and this is going to be an infinite set. So generally speaking, well, we can have finite semigroups that are finitely generated, but also infinite semigroups. Okay, and the problem we're interested in sorry, sorry, my son is shouting like crazy. Give me 1 second, sorry. Okay, so back to business. Yeah, so basically, if we're giving a set of generators, then we're interested. So the problems we've been looking at is bounding as a function of the input, the length of a given element in the semigroup. So which is just the number of elements, the smallest number of matrices I need from the generating set to obtain this matrix, and also the cardinality of the semigroup. So in very rough terms, basically whether it's finite or infinite. Yeah, so we want to decide, given this generating set, is the semigroup generated infinite or is it finite? And of course, it's clear that if we got a length bound here, then we also get a bound on the size, basically. I mean, if such a bound exists, yeah, then we also bound the size of the semigroup. So this problem, I mean, is interesting in its own right, but sort of in the 1970s, people started looking at these matrix semigroups coming from problems from formal language theory. So just to give a bit perspective, sort of where this problem originated from, I mean, where the problem of checking whether the semigroup is generated, whether it's finite or infinite, this comes from automata theory. And so here we have namely weighted automata. So they're just like finite state automata that we all know, but when reading a letter, we have a number here, and that we, whilst reading a word, we multiply the numbers that are labeled along the transitions. Okay, and so this in particular means that when we read a word, then the automaton maps this word to some value over the rationals, if the matrices are rational here. And the boundedness problem, that is the problem to decide whether this set is finite. Whether if I look at all words applied to this, whether this is finite, this reduces to a deciding finiteness of a matrix semigroup, and that's a kind of property that's interesting to look at for these weighted automata. Yeah, and so the way this reduces, well, we can look at the transition matrices for every letter of the alphabet, yeah, and then sort of I think you get the idea. Different words can give all possible combinations here, and then we look whether the semigroup generated by these transition matrices is finite. So that's roughly where this problem and the motivation comes from. Okay, and so what we showed is that if we're given a finite set of rational matrices that generate a finite semigroup, then the length of every element in the semigroup is bounded by, well, 2 to the n, yeah, n is here the n times n matrix, 2n plus 3 times the order of the largest finite subgroup of GLN, yeah, in Q, which is roughly bounded by 2n factorial. So I'm going to say something more about this in a second. Okay, so this gives us a bound basically of 2 to the O n square log n. So what's very nice, and also what wasn't known before, is that this bound does not depend at all on the number of generators. Yeah, it's a bound purely in the dimension of the generators, and also it's independent of the constants appearing in the matrix. And so sort of finding these length bounds, I'm going to say something more in a second, but this was a topic people started looking at in the 70s, getting very bad bounds. In the early 90s, Weber and Seidel considered matrices with non-negative integer coefficients, and they obtained a length bound of 2n log n, so that were pretty close. And they also gave a lower bound of 2 to the n minus 2. So this means, I mean, okay, of course one could still kind of tighten this gap further, but we're essentially, I mean, it's an exponential upper bound, and this is pretty tight, the upper bound we get. Yeah, and as I mentioned before, if we want to bound the size of a finite matrix semigroup, well, then we get this upper bound here, basically, but yeah, which is implied from the length bound. It must be the case. So the length doesn't depend on the size of the generators, but we can look at a very trivial example, basically, which shows that the size of the generated semigroup must also depend on the size of the generators. Yeah, if we take this example here, then the semigroup is MK union the zero matrix. Okay. Yeah, so this is the case. Also, if we're looking at real matrices, then it's very easily seen that we can't find such a bound that we have here, basically a bound only in terms of the number of generators and the dimension, because if we take, for instance, the rotation matrix here, yeah, parameterized by k, then the group generated by RK is of size k. This can be arbitrarily large, basically. So this sort of differentiates a bit real and the rational case. And so in terms of computational complexity, if we have a size bound, then of course we can very easily check whether the set generated, I mean, whether the semigroup generated by a given set of generators is finite by just yeah, taking all products up to the length and then looking if after we saturate, if we can get longer products that have not yet been obtained. And so, yeah, as I said, this depends on the size bound, and Mandel and Simon, and also independently Jacob in 1977 showed algorithms showing this finiteness problem decidable, and Mandel and Simon got a non-elementary lower bound. I mean, an algorithm with a non-elementary lower bound. So it's pretty pretty horrible. So we were pretty much better basically in that. For us, we can decide whether a generated group is matrix semigroup is finite in co-nx to the np. Yeah, so this basically means you guess a long word that is longer than the maximum length, and then you check that you can't obtain it shorter using a call to the np oracle. Now, the group case is nevertheless still, I mean, it's much better understood and has also been studied much longer. So as I mentioned before, in the group case, yeah, we get a size bound of 2n factorial. So this can be shown with relatively with elementary methods. And then Friedland and building up on Weisweiler, who build up on the on very deep results from group theory, established a bound of 2 to the n factorial for large enough n. And this bound is also tight for the signed permutation matrices that I mentioned earlier. Yeah, so they achieve this basically. And then there is also a refinement of this result. So Veit showed in unpublished work, building up on unpublished work by Weisweiler, that g to the n is 2n in factorial for all n except these few numbers here. So this was a manuscript that Weisweiler left behind before he disappeared in South America. And somebody, so you can find in this paper on the archive, somebody took his notes and then put them online. Also, in particular, I mean, even though sort of we have this 2 to the n factorial. Yep.
Is it known the exact values for those finitely many exceptions?
Yes. Yes, it is known. So you can look at the Veit article, but as I said, it's sort of unpublished. I mean, I think everybody accepts these numbers. Yeah. Okay. So even though in the group case, the group can be exponentially large, it's still possible to decide finiteness in polynomial time. Yeah, and there are also very efficient randomized algorithms known that actually work much more efficiently, at least according to Babaye-Beals and Rockmore, to decide finiteness in the group case. So as I said, we have a co-nx to the NP upper bound, which is much better than a non-elementary upper bound, but still there's work to do. So I think it's pretty likely that we can get better complexity upper bounds for the semigroup case. On the other hand, I'm also not really aware of non-trivial complexity lower bounds for deciding finiteness in the semigroup case. So I wouldn't be too surprised if the problem is, let's say, in NP or co-NP. But yeah, that's the situation as it is now. Yeah, so just to give you sort of a little flavor of how we obtain this result, I think for me at least the experience was really sort of the experience of standing on the shoulders of giants, I would say. Yeah, so we make heavy use, of course, of the size bounds for the group case because you saw already the g of n in the bound. We also use a graph of vector spaces that is associated to a generating set that was recently introduced by Khrushchevsky, Pauli, Worrell, and Rudnin, that they used to compute the Zariski closure of a set of matrices. So this turns out to be a very useful graph, and in particular, connecting it with basic properties of the exterior algebra gives us enables us to show this upper bound on the length of elements in the generated semigroup. So how does this graph look like? So suppose we're given a finite set of matrices of maximum rank R, yeah, then we take as defined directed labeled graph whose vertices are the images of all of the generators. For now, only for the purpose of illustration, we only consider those matrices where the rank is R. And then we have an edge between between two of these vector spaces, even only if v1 times m is equal to v2. Yeah, so that's sort of the graph of vector spaces. And I mean, due to the since v2 has also maximum rank R, it follows that v1 intersecting with the kernel of this matrix M here, I mean, must be trivial. Okay, and in particular, this means that actually v2 is equal to the image of M. So this means sort of a label in this graph or immediately tells you where you're going to end with. Yeah, I mean, you wouldn't even need to look. Sort of, if you see the label, you know you're going to end up in image of M. Okay, and sort of, I mean, just to give you, as I said, sort of, we're looking at path in this graph, and then we're looking sort of at properties that this path have. So, for instance, if we consider a path of consisting of k matrix products, where each of these matrices comes from the semigroup, and all of these images lie in different strongly connected components of this graph, then we can see that the image of every mi intersected with the kernel of mi plus 1 must be 0. Yeah, so this is pretty much coming from here. But we also see, since we can't go back in a strongly connected component, I mean, if they are all in different connected components, we can't go back. Then what we see here is basically that the image of all j with the kernel of mi is non-zero for all j less than I. Okay, and then this enables us, I mean, with not much thinking, to get a bound on the number of SCCs in this graph of 2 and choose R. Yeah, and sort of this is roughly sort of how, on a technical level, how these proofs work. And then with a similar reasoning, we can bound shortest path between two vertices in G and get a size of n over n choose R. Another observation we make is basically if we have cycles inside a graph, then they generate a group. And then this allows us basically to appeal to these bounds in the group case. And a final sort of ingredient of the proof is to, if we have an arbitrary path inside an SCC, then we can rewrite the path as an initial segment of cycles and the final loop-free path. So I have a little graphic here that is meant to illustrate this, but I think I'm a bit short in time, so I'm just going to sort of leave it here. So in the end, what sort of this line of reasoning and this strategy allows us to do is, we know that we obtain a length-bound full path in the semigroup that stays in the same strongly connected component of 2n plus 2, and then the group size minus 2. Okay, and then as I said earlier, we're only looking at, we've just been looking at vertices of rank R, but if we now include sort of all vertices of all the different ranks, we can sort of inductively build up on the smaller ranks and in the end obtain the overall bound groups that I mentioned before. Yeah, so this is, I mean, as I said, this is just a rough idea. So in particular, this gives us, in terms of computational complexity, an nx upper bound for deciding whether a given matrix is in the semigroup. So a result that was shown roughly 10 years ago by Almeida and Steinberg says that they consider deciding whether the zero matrix is in the generated semigroup, and they get a 2n square log n bound. So I mean, slightly better than what we have. In the non-negative integer case, a recent result by Kiefer and Maskell showed that actually you can obtain a length bound of n to the 5 for the zero matrix. And in particular, these matrices can be computed in polynomial time. So they can be found in polynomial time. So the question whether there is a polynomial upper bound for the zero matrix in the rational case is also an open problem. Okay, so this this brings me towards the end of my talk. So yeah, we answered a couple of questions, so we got rid of this non-elementary upper bound, but it's still sort of for some applications we're still interested in knowing whether the size bound can be reduced by one exponential. So we believe it is the case, but so far we haven't been able to doing so. And of course, I mentioned earlier, knowing whether a polynomial time algorithm for finite nets exists is also an open problem. Yeah, I haven't looked too deeply into the work of Babai, but it's likely that some of the techniques there are applicable. Likewise, the full complexity of the membership problem is also open. As I said, we have an NX upper bound, but again, this could likely be improved. Okay, so thanks for listening to me very early in the morning and very late in the evening. I'll be happy to take any of the questions now.